Okay, take two. Welcome to the Origin seminar again this week. Today we have Dr. Taylor Kutra talking about illuminating protoplanetary disk substructures and their effects on exoplanets. Taylor did their PhD in the Department of Astrophysics at the University of Toronto, working with Dr. Hu. And they are interested in disks that form planets, as well as disks that we observe around white dwarfs. In order to understand planet formation, the research has focused mainly on irradiation instabilities and how they form gaps and substructures in the circumstantial disk that we see with ALMA. And I guess that today we're going to learn more about that.
Yeah, so. Thanks. Awesome. Yeah, it's great to be here.
So before that, turn that off to me. I cannot handle that. X, yeah, and then maybe click.
Okay.
Okay, yeah.
There we go. And you can see it on the Zoom. Great. Okay, great. Yeah, so I'm going to be talking about a lot of the work that I did at the University of Toronto. I'm currently at Lowell Observatory, just up the road. So stoked to be down here to meet everyone. And here we go. So central motivation to all of this, basically everything I do is this beautiful gallery of protoplanetary disks from the D-Sharp survey. And my favorite thing about these is, I think in the last 8 years or so, protoplanetary disks have become this thing that instead of this passive background that planet formation sort of happens on top of, that we're seeing them more as an active participant in the process and the way that they in the structures that exist in them and how those can affect the populations of exoplanets that we can detect after the disk dissipates. And so in this talk, I want to talk about sort of two big questions that have informed my work over the past number of years. The first one, what is the origin of these substructures in protoplanetary disks? Mainly here, I'm talking about sort of the gap and ring type substructures, but nonlinear effects can do lots of fun things. And then I'm also going to talk a bit about sort of the impressions that a protoplanetary disk can leave on fully formed populations of exoplanets. So starting off with the first one, everyone's sort of knee-jerk reaction when we see a gap in a protoplanetary disk is to throw a planet in it, for good reason, right? Because these planets can carve out these gaps really efficiently. But there seems to be this sort of occurrence rate problem, right? For lots of these gaps, we need sort of cold Jovian type planets on, distant orbits, 10 to 100 AU. And that's not the most common type of exoplanet. But these gap and ring type substructures appear to be basically ubiquitous. So there seems to be a non-commensurate problem with the occurrence rates. And, even if these two occurrence rates really did match up, there's another problem when we tell the story of planet formation, is because typically when we want to turn these micron-sized dust particles, sub-millimeter-sized dust particles into larger planetesimals, we invoke things like the streaming instability. And in order to successfully have streaming instability, you need this enhanced dust to gas ratio, which is, conveniently found in these dense rings in the protoplanetary disks. And so we sort of, we need these dense rings to make these planets, but seemingly need a planet to make the dense rings. And so we walk ourselves into this infamous chicken and the egg scenario where we have to ask, so what comes first? The dense ring that's required to, trigger streaming instability that causes planetesimal formation that then goes on to make planets, or the planet that is needed to make the overdense ring. And so in addition to that, in addition to the sort of observed substructures, there are two other really well-known phenomena in protoplanetary disks that are problematic for planet formation. The first of which being dust drift. So these larger dust particles that sit in the midplane of the disk only really feel the gravitational interaction from the star, whereas the gas of the disk also feels a pressure term, also feels pressure, gas pressure. And so the gas moves slightly slower than the dust. Dust faces a headwind, loses angular momentum, and will spiral in towards the star. And that's the same material that we need to stick around in order to actually make planets. And so a really convenient thing about these annular substructures is they're really dust traps. They're regions where this migrating dust has spiraled in, and then typically a feature of the disk, like a pressure gradient change or pressure bump, will stop that inward migration and dust can accumulate. And then the last one is actually a really fun problem that I don't think people talk about very often. It's this issue of lofted dust. So these are the small, like micron sized. Oh, my save didn't change. So let's say microns, or sorry, millimeter dust lives at the midplane of the disk, right? These are the larger grains. They settle quickly to the midplane. But the micron sized dust, we think of being as like entrailed in the gas and sort of determined its entire all of its motions are determined by the gas motions. But really, if you look at the settling timescales for even this micron-sized dust in really low density environments, that would be the case at several scale heights off of the midplane of the disk, where sort of the optical surface is. The settling time is actually really quick, and so it's a problem because we see these disks having these nice flared shapes. And these micron-sized dust grains are responsible for, heating the disk, maintaining that flared shape. But if they settle over, timescales that are shorter than the disk's lifetime, then you take your nice, like fluffy flared disk, and it settles and you collapse it. So we might need to replenish these small dust grains up above the optical surface in these inviscid disks. And so keeping all of that in mind, we, like all good theorists, try to solve all the problems all at once, right? And so one thing that's common to every protoplanetary disk is that they're being illuminated by their central star. And so in most of the disk, the heating from the central star is really the dominant heat source. And so this is the classic Ching and Goldreich question that's on every qualifying exam. So when I think of a disk, I think of, this like nice flared surface. This is the optical surface. It's where the gas becomes opaque to photons from the star, from visual light. But what's really happening on this optical surface is there are these micron-sized dust grains, the ones that we need to replenish, the ones that are really important, and they act like little mirrors. They absorb incoming stellar radiation, and then they re-radiate it isotropically. Half of that is lost to space. We can, image that in scattered light, plus some other physics, but mostly that's what scattered light is. And then half of it is pumped down towards the disk midplane, and that's responsible for heating the larger dust grains that are sitting at the disk midplane. This is why the disk has a temperature. Then, of course, those larger dust grains at the disk midplane are hot, so they're radiating like black bodies to cool themselves. That's what we look at when we see like ALMA thermal continuum emission. And all the while the disk is maintaining some sort of hydrostatic, vertical hydrostatic equilibrium that keeps both of all of these things in addition to gravity in check. And so what I want to do is I'm going to convince you that these disks are actually unstable to temperature perturbations. So if I'm to add, a small temperature perturbation to the midplane of this disk, the gas will expand. And what that'll do is it'll slightly kink the optical surface above and below the disk. Now, if we think about sort of what's happening to our little mirrors, interior and exterior, the amount of starlight they're receiving is the same. But at exactly this spot where, the optical surface is at it, the slope of the optical surface reaches a maximum, all of a sudden, the disk has sort of poked its head up above the rest. Another way of thinking about this is that the incident angle of the stellar photons is closer to 90 degrees. And if that incident angle story sounds familiar, it's because that's how the seasons work on Earth, right? The reason that it's hot in the summer isn't because the Earth is closer, right? It's because the incident angle of light from the sun is, more overhead. We're packing more photons into this small area. And that's exactly what's happening at that location on the disk. And so now, because this portion of the disk is receiving more starlight, it's going to deposit more starlight, deposit more heat down towards the midplane of the disk. And that perturbation is going to grow. And then in this outer region, this is where the disk is sort of experiencing its winter. Now we have, the same amount of starlight spread out over a larger area. And so this will cool in the shadow. And so I hope you can see here that, this wave, this thermal wave, is not only going to grow, but it's also going to move inward. And so that's what it does. And that's what folks found. So two sort of, seminal works about this were from Watanabe Lin and Yoshimura and Yoram Lithwick. And they found these thermal waves. They're sort of excited in the outer part of the disk at about 30 AU. They grow, they propagate inwards, and then they dissipate. And both of them did it through sort of like a radiative transfer iterative method. And so there's a big asterisk to this sort of picture, is that they didn't include two really important phenomenon. Hydrodynamics, because these disks are fluid systems, and vertical thermal diffusion. So the midplane of the disk, in addition to being, optically thick to the light from the star, the midplane of the disk can also be optically thick to the light from the little mirror sitting at the surface. And if that's the case, then the heat transfer towards the disk midplane won't be exactly like instantaneous. It'll be controlled by thermal diffusion time. So the heat has to diffuse through that gas. So two other folks more recently tried to relax both of these assumptions. Mellon-Fuchsman et al. And the Polachenkov, they both use sort of like two different versions of radiative hydro, and tried to excite these thermal waves. And both of them weren't able to do it for different reasons. But as you'll see, we do something very slightly different to what they do, and we get dramatically different results.
Can you just quickly describe what did I'm familiar with the Mellon-Fuchsman work, but how different was the Pavlyuchenkov?
They just used their own code, basically. Yeah. They had a similar setup. They had a different initial configuration. We'll get to that later. So the surface density profile was slightly different. They actually simulated a radiated inner rim. And I think they didn't use this like the 2 moments method with the Eddington M1 closure. They had their radiative transfer was different as well. Yeah. Okay, so to do this, we use a modified version of Athena++ in two dimensions, so R and theta, and designed this routine to incorporate stellar radiation. The setup can be broken into kind of 2 steps. First, we trace the rays coming from the star. And so I've drawn the slide sort of in spherical coordinates. So starlight comes in along horizontal lines. And so we integrate along every ray and compute the optical depth. We also include, because we don't want to simulate, the inner highly irradiated inner rim that has, it's magnetized. There's lots of different physics going on for the inner rim of a protoplanetary disk. But the important thing is that they usually extend a shadow to about an AU. And so we add some initial like tau value so that we just establish a shadow coming in from the inner boundary of the computational domain that extends to about an AU. So then, we start from that initial tau value, we compute the optical depth along the radial lines. And then the flux of photons is, simply, it just exponentially decays with the optical depth. And then if you take the divergence of that flux, you can get the amount of energy that's deposited into the gas, which is represented here with these contours. So this is really where the energy is being deposited. This black line across the middle is the optical surface. So there's like a finite length and width where the energy is being deposited. Then we take the next step is sort of dispensing the heat. So the first thing that we do is we vertically integrate these contours just to try and get a sense of, how much energy is being deposited per column of cells. And so we vertically integrate. Then we have a cooling term on the end of our thermal equation over here, a cooling term, which accounts for, the midplane, the dust midplane emitting. And we call the temperature associated with the amount of energy that's deposited into the individual column of cells, the forcing temperature. So really, this is just a relaxation equation. If there was no added hydrodynamics, every column of the disk would relax to the forcing temperature over the thermal time, tau thermal. on the bottom there. And so this is, again, our vertically isothermal assumption. So we're not doing that sort of process of thermal diffusion, vertical thermal diffusion, where the disk midplane is optically thick to the light from the micron-sized grains on the optical surface, where it's instead just assuming that the disk is, optically thin vertically, and so it can maintain this vertically isothermal state. I'm sorry. And then we just add or remove the energy based off of the cell density to make sure that we heat the disk, we heat the columns of cells.
Sorry,
Yeah.
the vertically isothermal condition is
Yes.
valid from the tau equal 1 surface all the way down to the midplane, right? But above that, you have a different temperature.
No, the whole computational domain. We'll talk about this later, but the density of the gas above the optical surface is so low that we don't think it's really a problem there. There's a difference, there's gonna be a difference in the temperature. That's not how the gas above the optical surface behaves. But it's so low that we don't think it actually affects the heating terms that we calculate.
So there's no vertical temperature gradient in all the setup.
No, except for, any changes to the vertical temperature gradient due to like compression. Yeah. Thanks for that. So then there's two other things that we consider for the treatment of the thermal physics. The first of which is that grains at the disk midplane, they're not heated by only those grains directly above them. Adjacent grains will also contribute. And so that's what we're kind of seeing pictorially on the right. And so the heating function, the forcing temperature will be smooth. And that smoothing, that amount of smoothing will depend on how far the optical surface is away from the disk midplane. And so in order to sort of emulate that, we just add Gaussian kernel smoothing to the forcing temperature, where the width of the kernel is the scale height of the disk. And so if the optical surface is further away from the disk midplane, the temperature has the forcing temperature has a smoother profile because it's being irradiated by sort of more of these lights. Next, if you're at a portion of the disk that's like in a very deeply shadowed region where maybe, hot rims are at distances larger than the optical surface height, you still won't ever reach a temperature of 0. And that's because you have these whole hot columns that are radiating isotropically as well. And so the heat from those can penetrate even the most shadowed regions. And so in order to sort of emulate that, we just introduce a minimum forcing temperature so that we don't ever cool our disk down to sort of very, very low temperatures. And we have some results. Here's some results. So this is how the fiducial disk reaches the steady state. On the bottom, you're seeing the midplane temperature over time as a function radius on X and time on Y. And the top is the optical surface with darker colors being later times. And so you can see we start off from, just a smooth temperature profile, and perturbations develop. The thermal wave moves in slightly, and then it stalls. And then a second thermal wave forms, moves in, and stalls. And same with the third. And then at the end state, the optical surface resembles that of a staircase, where we have these shadowed regions, these irradiated hot rims, followed by punctuated with hot rims and shadowed regions. So it was surprising, but the interesting thing about our vertically isothermal assumption is that it's not valid during sort of the early evolution of these thermal peaks, but it is at the steady state. So if the disk can get to a location where it has these irradiated rims, it will stay there. It is steady. But of course, we wanted to, well, I'll show you a better, more detailed view of this disk first. So over here, maybe I should point with your mouse because people are all online. So over here, this is the irradiative flux. So this is where the energy is being deposited in the disk. The overplotted white line in all of them is the optical surface. Here we have the vertical temperature profile, and then over here is the gas density. And we'll show you this animation over years. So the thermal waves develop, move inwards, and then stall. And this is how the disk is, vertically isothermal. So of course we got this, and we initially were like, okay, is there something wrong with our treatment of the thermal physics? Like, that's what we're trying to do. Did we do it correctly? So we immediately ran it through like more sophisticated radiative transfer code to see if the end state was actually in a thermal equilibrium. And so this is our comparison. On the left here, you're seeing the midplane temperatures of our simulations in blue and RADMC in orange, and then the vertical temperature profiles for both of the simulations. And there's generally pretty good agreement in most cases. And so we are convinced that, the end state is actually in a thermal equilibrium. There are two, glaring discrepancies, one which you asked about, these temperatures at high altitudes. The gas density is so low up here that we don't think that this actually affects the irradiative flux that the disk is receiving. And the reason it's different here is because we even treat the gas above the optical surface with this vertically isothermal assumption. And so that's why we're getting that. There's also at the upper boundary of the computational domain, there's compressional heating from, imperfect boundary conditions. And so, but if the density is so low that we're not concerned about it.
I'm a little bit confused about, maybe it's the coordinate here, right? Look at that last plot, your Athena field. It does not look vertically isothermal.
This one?
Yeah.
So when we say vertically isothermal, like we're talking about below the optical surface, largely.
Right, but so I guess I'm trying, when you say I understand the diffusion equation you were using certainly is consistent with the disk that approaches vertically isothermal. But you're not actually enforcing that the temperature has to be the same at every height. You're evaluating each cell independently as a function of height.
No, we're evaluating each cell based off of the midplane temperature and then adding energy based off of the individual cell density.
But is it just because you're showing that in theta coordinates that I see curvature?
No. So the point of these two is that sort of below this line here, these sorts of bands that we're seeing.
It's not perfectly vertically isothermal, right?
No.
So that's
because of the hydrodynamics. It's never.
But that's what I'm trying to understand.
Okay.
You're not enforcing that the temperature is the same. When you say vertically isothermal assumption, it's in the construction of the diffusion equation.
Yes.
That diffusion equation is consistent with what you would expect for a disk that is perfectly vertically isothermal.
Yes.
Nevertheless, your simulation evolves away from it.
Yes, because we don't enforce, like it's got the added hydrodynamics. We don't force it to be vertically isothermal. We just create the thermal physics. Yeah. Okay. Cool. Thanks for clarifying. Yeah. So we have that difference up there, which we don't think is going to significantly affect the amount of irradiation that the disk receives. And then more importantly, though, we have this small difference in the midplane temperatures of the two simulations. So the annuli just sort of inward of our irradiated hot bumps are warmer in the RADMC simulations because of the geometry, right? If you have like this hot rim that is, it's physically extended higher above the optical surface, it's going to heat the gas just interior slightly more than it is going to be the exterior.
So in the midplane, there's no diffusion here, right?
No, there's no thermal diffusion.
It's all, so in the simulations in Athena, it's a relaxation term.
Yeah.
The whole domain.
Yeah, and then we're just comparing to RADMC. So that could be a problem. But you have to sort of account for the entire geometry if that's the problem you want to solve.
And then the major difference for the 2AU and.
Oh yeah, this is from the inner shadow.
Right.
So we this is our minimum temperature profile that we set just because we're we don't fully do the whole geometry. So we just set a minimum temperature profile that's some fraction of the chain gold rate solution. Whereas RADMC, actually will cool the gas in there. Yeah. Okay. So yeah, then we tried to make the waves stop stalling, right? Because that's the big difference between the linear theory and these simulations. So the first thing we did was this parameter study. We looked at first the opacity. The way this manifests is, the height of the optical surface and the location of that first thermal peak. And the thermal peaks get sort of smoothed out, as I said, as the opacity gets higher because the optical surface is further away from the disk. But the important thing here is that these all reach this sort of steady state where you have this at least one hot rim followed by, more smoothed out hot rims that take place at larger distances. Then we changed the width of that smoothing function because it was kind of an arbitrary choice. And so we say, okay, what if we create a disk that has the smoothing function is much longer. So, and that's what you're seeing with the blue, and we still get a steady state. We then, turn the smoothing function to 0 so that the temperature of every midplane cell is really just determined by the amount of gas that's deposited directly above it. And we get this orange curve. It's very different, but it's still a steady state. And it's actually a really interesting one. We changed, the initial temperature profile. Again, still saw these steady end states. And then lastly, we also changed the thermal time because we noticed in our simulations that it had sort of this very distinct inside-out evolution. The first peak would form, it would cast a shadow, it would cause the formation of the second peak, would cast a shadow, which would cast a shadow and cause the formation of a third. So, we increased the thermal, one thing we did, aside from that, we increased the thermal time by a factor of 10, just to say, okay, if there was thermal diffusion, how would that sort of manifest in this? Well, it would just take longer for these disks, for this disk, for the thermal waves to form. And so we did that, we still get the identical end state, just takes longer. And then to deal with this inside out problem, we actually changed the slope of the thermal time with sort of a arbitrary function so that the outer disk responded to the heating faster than the inner disk. In a normal protoplanetary disk, the thermal time in the inner disk is faster. The inner disk responds to the heating from the star quicker than that of the outer disk. But we switched it just to see if we could, make a different kind of evolution. And we got basically the same thing. So even though the outer disk responds to the temperature between the forcing temperature and the midplane temperature, they reach equilibrium before the inner disk, we still get this inside out formation of thermal peaks. So summary is that they all reach this steady state. So our next question was, well, is it this inner shadow that we've chosen to put at the inner edge of the computational domain? And so we did that. This is what the Pavlyuchenkov paper did. This was another big difference besides their radiative transfer routine. We used this surface density cutoff. And so instead of having this shadow that comes in as an initial condition, we actually simulate a highly irradiated rim. And that's what you can see here. So the temperature of this rim, is upwards of 200 degrees Kelvin, but it still casts a shadow, which leads to the formation of these further thermal peaks at larger radii. And then because we wanted to, compare more directly with the Pavlyuchenkov paper, they used a 5 solar luminosity star, which is really bright. And so we did the same thing. And it creates this rim that is so highly irradiated. If you look at the top, the optical surface is close to the upper edge of the computational domain. And so what happens is this rim is so hot, it puffs up physically so much that it casts a shadow out to beyond 20 AU. And so we think that the reason that this doesn't develop any thermal peaks is not because it can't, it's because the entire disk here is in shadow. And for comparison, this is the commensurate plot from the Pavlyuchenkov paper. They also have this really highly irradiated rim, which we think, casts this humongous shadow through the entire domain. So the next thing that we, wanted to look at to see if it was causing the waves to stall are the meridional flows, the fluid behaviors in the R and Z plane. And so that's what I'm going to show you here. So these are streamlines, so that you'll see the direction of the flow. They're also normalized by the local sound speed to times 10 to the -3, so it's small. And I'll play this for you. It's kind of a choppy video, but you can see zoomed in on one thermal wave. So as the thermal wave sort of develops, you get this sort of like upwelling of gas just interior to it. And then we start to reach the steady state, and there are still some flows, but the magnitude is really small. It's quite small. But especially towards the optical surface, the fun thing is those meridional flows are persistent even into the steady state. And overall, the magnitude of these flows is less than 1% of the local sound speed. So we don't think that this is really enough to sort of carry the gas away from the inner part of the forming thermal wave such that it stalls. We're skeptical. We don't think of that. And I'll just say one more thing that's kind of fun. I wouldn't trust this entirely because this is during the early evolution of the thermal wave, but the pattern is distinct too. So in the early evolution, this is just 2 snapshots from that. You have this like upwelling, this fountain-like substructure of the meridional flows, whereas for like an embedded planet, you typically think of like a drain effect on the meridional flows. And then again, these are the meridional flows at sort of the steady state. Where they're small, but they're still persistent. Okay. And then we just wanted to know if the final end state was susceptible to further development of the irradiation instability, if you could have like more thermal waves propagate on top. And in the paper, we do some stability analysis of that. And long story short, we find that the steady state that we find is stable to further irradiation instability. So in general, we don't know. We don't know why the waves are stalled. We think that it's a physical end state, but we're unsure. So if it is a real end state, it'll make observables. You'll be able to see it in these disks. And so we took our, end density profile and temperature profile and ran it through, again, RAD-MC to create these simulated images in the scattered light on the left and the thermal continuum on the right. Yes. You can get these sort of annular substructures on scales that are small, but comparable to the kinds of substructures that have been found in, compact disks as of the last year or so. So that's fun. Another great thing about this is that the steady state exhibits this local pressure gradient minimum. I'll use this here and here, just internal to sort of the thermal peak. So you can see the thermal peak there. And there's a local pressure gradient minimum. And while this won't completely stop the migration of dust, it will slow it significantly. So you can have sort of a dust like traffic jam, almost is what I'm envisioning. And then these meridional flows, like I said, depending on their strength and the settling timescales, might be able to help loft these little dust grains up above the optical surface to replenish them. Okay, so that is that.
So
Yeah.
before you switch, I wanted to ask you a question about your trying to explain why the wave stopped. So initially, the way you introduced it, it seems to me that it was the generation of the wave was the lack of balance between the heating and cooling and surface. So eventually, that creates the wave. But have you checked, for example, the balance of heating and cooling as the wave propagates? And if it's reaching a thermal equilibrium at that point, and that stop the...
Yeah. So we have these, we have these movies where we have the forcing temperature and the midplane temperature. And when the wave is propagating, they're doing what we expect. We expect the forcing temperature to be sort of out of phase, slightly inward of, and then it reaches sort of the the outer edge of the shadow that's cast, and the forcing temperature stops moving. It bounces, it kind of like bounces off of the shadow, and then the cooling term catches up with it. And it's something to do, I think it's something to do with like this sort of region of the disk that's just coming out of the shadow. Something weird about the forcing temperature there. Yeah.
And maybe the second quick question or comment is that have you validated these waves with the linear theory? Yeah, there was a paper from Jackie here on Midway where they show the wave numbers, for example, waves.
Yeah.
And thermal time scale, and is this in agreement with any of those?
Yeah. Yeah, it falls, if they fall, the spacings of them, all falls within the accepted. Yeah, they're sort of wave numbers. Do you have a question?
Yeah. So all of this is sort of the consequences of a temperature perturbation that appears in the disk.
Yeah.
And it seems to me that your, ridges reach steady state very quickly, a few hundred years based on the simulations you showed. So, but we know that not all disks have these exact structures. So what do you envision being the origin of that temperature or temperature perturbation?
Oh, yeah. So from the linear theory, right, they can be infinitesimals, right? So in a perfect disk, an exothermic reaction can trigger one of these. In these simulations, we have like a very distinct initial perturbation. It's that shadow. It's the shadow coming in from the inner computational domain. Because we're essentially saying this region of the disk, we're going to cool it immediately, and then the thermal waves form outside. So it's not surprising that we get our sort of first thermal peak just external to the shadow that we impose on it. But that's the reason that we wanted to, get rid of that shadow and actually simulate this in a rim, because, the inner rim of a protoplanetary disk does extend the shadow to about an AU. And so it's a realistic assumption to make for the inner edge of the domain. And even when we simulate that inner rim, we still get the thermal peaks that arise outside of it. So it's like physically, theoretically, anything can make the perturbations, right? They're infinitesimals. But physically, the thing that really can drive this whole process is that inner shadow from the inner edge of the disk. Okay. Does anyone have anything?
Yeah, sorry. Can you just explain a little bit where these surface density curves came from? Was it initially smooth, or did you? Yeah.
Yeah. So you're talking about the top. Oh, these surface density curves. Yeah. Initially it was smooth. Yeah, it was just a normal 150 gram per square centimeter with power law. And then we integrate the density vertically integrate the gas density, and then, assume some gas to dust ratio to get the surface density. Or no, we don't assume that. This is the gas surface density. And it's divided by the initial value. So it's just a % change in this plot. So in addition to these surface gradient, pressure gradient minimum, we get surface density enhancements. Yeah.
A quick question. It's not exactly. So you're saying that the shadow of the inner rim cause, I think most of the disks have inner rims. So part of every disk could establish waves by the process you're showing. So what is other methods of the process that would prevent disks from forming? Because then all of the disks should show these waves.
Right. Yeah, that's a great question. I guess the optical depth of the disk, like if it's a really thin disk, the inner parts of these disks should be quite thick. But if this is real, then it should affect a lot of disks. Whether or not it's real, we need to do real radiative transfer simulations that can, reproduce sort of the optically thin limiting case. But yeah, and it should, like, there's tons of other places that it would be really important, like the migration of an embedded planet, or anything that happens in a gap. Yeah.
Okay, so I guess that's my question is.
Yeah.
Didn't the Mellon-Fluxman paper do 2-moment radiative transfer? So do you understand the differences between the two results now?
Yeah. Let's chat later. I can show you in our paper, we take basically their end state, and we do the same thing that we did with our end state, and we ask if whether it's in thermal equilibrium using RANMC, and we didn't find really good agreement. So I can show you that later.
But I mean, a 2-moment scheme should be more, like, I would expect that to be more reliable than an approximation of a diffusion equation that already has a thermal assumption. So what's the reason to go away from a 2-moment method toward this method? Because
they calibrate their 2-moment method in one, like the optically thin and thick regime. They don't calibrate it for the transition between the two, which is like the fundamental big difference here. Well, what's the fundamental problem with this problem? Is you have regions of the disk that are optically thin where the heat transfer is instantaneous, and then yeah. So, but I can show you the plots later from just our analysis of their end state. Cool. Okay. But yeah, I'm more than happy to talk about this. Really stuck about this project. Okay, so I'll go over this pretty quickly. So the next thing that I want to talk about is just this work that we did, which has a lot of connections with folks at U of A, about the impressions that a protoplanetary disk can leave on the populations of fully formed exoplanets. So to think about this, we look at this particular type of planet. We call them Kepler planets just because they're the most numerous find from the Kepler mission. People also call them super Earth sub-Neptunes, and they occupy this really interesting place in the story of planet formation, because we typically think of planet formation as like a series of dust conglomeration and then oligarchic growth, where we accumulate planetesimals to create sort of larger rocky bodies. If those rocky bodies are sticking around, are formed while the protoplanetary disk is still around, you get hydrodynamic gas accretion onto them. They accrete these primordial atmospheres. That's what we think of when we think of Kepler planet, super Earth, sub-Neptune. And then if those objects become large enough, they undergo, if the rocky mass in them becomes large enough, they undergo runaway gas accretion and become sort of a Jovian planet. And so when we think of the Kepler planets, we think of them as sort of the failed cores of Jovian planets. So yeah, the Kepler planets also have, another thing going on. There's a reason that people call them super Earths and sub-Neptunes. The radius distribution is bimodal, and the densities for either of them. The smaller ones are probably rocky with little of this primordial atmosphere remaining, and the ones that have about 2.4 Earth radii likely have this sort of extended hydrogen-helium envelope that sort of inflates their radii. And so you might wonder, how do you end up with these two distinct populations of planets if the process of planet formation seems smooth, right? You don't expect it to be so carved out. And there's sort of like two favorite versions of this. The first of which is photoevaporation, where light from the star essentially blasts off the atmosphere of a planet that's either too small or too close, or core powered mass loss, wherein the core of the planet is so hot that the atmosphere is hot and then hydrodynamically escapes as well. And so the point of this is that either way, this bimodality is carved out sort of after formation. There's this really interesting paper that Eve Lee wrote last year for like a primordial radius valley. But again, in that picture, we're still forming cores of these planets that are like a uniform growing distribution. They're still sort of like monotomically increasing. It's just more of the gas behavior and the gas mass that's really affecting the like primordial radius valley that she wrote in that paper. And so if the Kepler planets really are these failed cores of Jovian planets, we would expect them to kind of act the same way. That we would expect them to sort of prefer the same stars. And we've known for a long time that giant planets, they strongly prefer metal-rich stars. This is from Fisher and Bellinetti. The occurrence rates of these giant planets is much larger around metal-rich stars. And so if Kepler planets are simply, failed giants, you would expect that they kind of follow suit, but they don't. So this is a figure from Weizu's 2019 paper. Here you're seeing, there's a couple things that you're seeing. The open circles are the occurrence rates over all of these metallicity bins for all of the planets, including giant planets. And the filled squares are for just the small planets, so just with radii less than 4 Earth radii. And where there's two, sorts of important parameters for this, the number of planets per system and the number of planetary systems. I'm concerned with really the number of planetary systems, not what the multiplicity is of these systems. So we're really looking at the orange. And so the point of this is just to say that the slope of the line that connects, the empty circles and the filled squares is lower for the filled squares, right? So the trend is weaker for the Kepler planets. And that's matched with like a bunch of different surveys of these types of planets. And so we saw this and we wanted to know basically why this connection was so weak. And so we took this population of 696 planets orbiting 492 stars from the California Kepler survey. And, like Wei did in that 2019 paper, we first asked if the super Earths and sub-Neptunes prefer the same kind of hosts, which you would expect if they are basically the same population of planet, they would prefer the same kind of host. And by comparing the metallicity distributions of the hosts of super Earths and the hosts of sub-Neptunes, they're indistinguishable essentially. But when you compare the metallicity distribution of all of the stars that host super Earth sub-Neptunes to a bunch of stars that aren't known to host transiting planets like those in the Lowell survey, you do find that they are significantly metal rich with some p-value that's small, right? But again, we want to know exactly how metal rich are they and why, right? So we made this forward model where we essentially said, we've measured this difference between the metallicity distribution of the hosts of Kepler planets and normal stars. And we have only, 500 hosts. How strong of a relationship is that given the significance of the detection we've made? So we generated mock populations, and then, compared it to our sample. So that's what you're seeing on the bottom here. Gamma, this is the scaling factor. So if, the fractional planets goes as stellar metallicity to the power of gamma, that's what we want to know. And what you're seeing on the bottom plot is, if gamma is really strong, the population really prefers metal-rich stars. You don't need that many planets to make the kind of detection, to see the difference in the metallicity distributions. Whereas if gamma is 0, you essentially need infinite planets to show that the distributions are different, because they're not. And so we did that. We made this forward model and we compared it to, our sample size. And we figured out that this value gamma is about half. And for reference, for giants, it's 2. So it's markedly weaker than for the giant planets. And so we introduced one more twist to try to explain this difference, and it's binarity. So we know that planets tend to avoid close binaries. What you're seeing on the left here is a comparison of sort of, the number of stars that have close-ish binaries, less than 100, or there, a couple thousand AU. And then in the overplotted red histogram is the number of the occurrence rates of binary systems with planets. And you can see that there's a marked difference between the blue curve and the red curve at small orbital separations. And so that, that and a bunch of other things lead us to believe that planets avoid these close binary systems. And then a couple of years ago, Maxwell Moe and Caitlin Kreider, they did this work about how binaries prefer stellar metallicities. It turns out that there are more single high metal-rich stars than there are low metallicity stars. And so we wanted to know, okay, does this already weak correlation for the super Earth, the Kepler planets, does it disappear if you consider that these planets don't form in systems with binaries? And so when we took that into account, gamma got smaller, almost consistent with 0. So here we have, the fraction of planetary systems going up, the fraction of close binaries going down. They essentially add up to, an even population. And so this was interesting because, first off, to first order, it means that, low and high metallicity stars are sort of equally likely to host super Earths of Neptunes. But it also implies that, the protoplanetary disk doesn't need that extra boost of material that you get with a high stellar metallicity. Typically, people take the stellar metallicity to be a proxy for the amount of solids in the disk. And so with increased solids, they expect more planets, but that you really don't need that to form these Kepler planets. And so just to paint sort of a crude picture of what's going on, we made this sort of phenomenological model where we just said, okay, we have this population of protoplanetary disks, and the spread in masses is huge, much larger than the spread in the metallicity. And so that's what you're seeing here. And this is sort of a plot of where these different systems occupy in the parameter space. So we take these, this mock disk population, and we assign sort of the outcome of the system based off of a couple of conditions. And then we want to compare, see how well we can reproduce the observed occurrence rate trends just by considering sort of the amount of solid mass in the system and the propensity for binaries to prefer metal poor systems. And so that's what we did here. We chose the super Earth, sub-Neptune, and Jovian difference because, in order for runaway gas accretion to happen, the core mass of the planet needs to be, 10 to 20 Earth masses, and the size of the Kepler planets is about half of that. And that's not a big difference, but they have this really distinct difference in their metallicity relations, their occurrence rates and their metallicity trends. And so one possible solution to that is to argue that, if the solids in the protoplanetary disk make a Kepler planet first, and then they make these Kepler planet first, and then only if they have enough do they make these larger Jovian planets. And it's maybe not such a ridiculous thing to think because there's been a number of surveys that have found that these full Jupiter type planets are formed quite frequently in systems with interior Kepler planets. So only if there's enough mass do we form a Jovian system. And anything else that doesn't have quite that enough material instead forms these Kepler systems. And none of them form in systems with binaries. And then we just see if we can reproduce that metallicity dependence. So here on the right, you're seeing, the data points for the binaries, the Jovians, and the Kepler planets, as well as the occurrence rates based off of just this very simple phenomenological model. And there's reasonable agreement. We've normalized them so that the overall populations have the same occurrence rates, but it's the trend that we were surprised that you could reproduce really easily. And there's a million physical processes that could affect this outcome. But the success of this kind of simple model really likely stems from some fundamental role that the abundance of solid material in the protoplanetary disk has in the role in planet formation. And yeah, I just wanted to plug, I'm in Flagstaff now. We work on young binary disks and young binary systems. So I'm running out of time, but so if you're also interested in this, come talk to me. I'd love to chat. I'll leave this up and take some more questions.
Are there any questions from the audience or online?
Well, I think you could probably talk about it briefly.
Yeah. Yeah, so, okay, up in Flagstaff, I'm joining Lowell Observatory as a part of a team that's working on this sort of like long-term project, looking at disks and young binary systems. It's a really interesting physical setup because, you know, you have a circumbinary disk, which is typically quite diffuse, and then you can have 1, 2, however many circumstellar disks. And it's a tumultuous place, as you can imagine. These disks are very small. They're tidally truncated by the secondary star. There's like continual gravitational torques from the circumbinary disk. There's accretion. But nonetheless, some of them do still form planets. It's definitely, like I said, not the norm. But some of these disks are massive enough and stick around long enough in order for planets to form. And so we're just trying to figure out why. We have a combination of a ton of H-band spectra from Keck, as well as precision astrometry that dates back like 30 years. It's wild, as well as ALMA data to look at these systems. And so just wanted to plug that because I know that there's lots of binary people around here somewhere. Cool. Thank you. No problem.
How far away are some finite systems that we're observing?
All the ones that we have ALMA data for are in Taurus. Yeah. Yeah. But we have ones in like Ophiuchus and yeah, all over the place.
So for the first part of your talk, you ran meridional slices, assuming exosymmetry.
Yeah, so they're 2D simulations. Yeah.
How do you think adding the azimuthal direction will change your result?
Yeah, so great question. Adding a third symmetry, because the end state has this pressure gradient minimum, it's actually probably unstable to Rossby wave instability, which can create these large like non-axisymmetric dust traps. So yeah, there's tons of things to do in 3D with this. Yeah, absolutely.
In these simulations you ran, did you see any other hydrodynamic instabilities like VSI or convective overstability?
Yeah, no, we didn't see any VSI. We computed like the growth magnitudes, and didn't get any VSI. Okay. Yeah. We're doing like inviscid simulations as well. So
I just asked because
yeah,
the setup looks similar to people doing VSI and convective overstability stuff.
Yeah, no, definitely.
Yeah, we think the inviscid case with the vertical isothermal equilibrium would be the most likely to develop the BSI. So, yeah, we can talk later. Maybe something else on the setup that is not showing up in the velocity field, but not in the
Yeah, because I computed the maximum growth rate. There's a simple based off of the velocities. We didn't find anything big, but yeah, let's try.
Okay, then if there are no further questions, let's thank Taylor again.